Okay, so reviewing homework from last night. Number 1, you did, and it looks like this. In the list of things that the book did, they found the derivative and found where it was undefined. They found the second derivative where it was undefined. Horizontal, vertical asymptotes. I would have made this one fraction to find horizontal and vertical asymptotes. I don't know what you did. Like I would have found a common denominator and put it all in one, because that way it's easier to tell top and bottom and get the horizontal asymptote being y equals -3. So if you want me to explain that, holler now and we can write it down on paper. Yes, okay. So let's find some paper. So if x minus 2 is a common denominator, I'm going to multiply this by x minus 2 over x minus 2. Now they both have a common denominator. I can say y equals 1 minus 3x plus 6 over x minus 2. Combine it. So now I have negative 3x plus 7 over x minus 2. Now you're like, okay, vertical asymptote is x equals 2. Horizontal is they have the same degree. You can see it because it's one fraction. Harder to see before. If you wanted to think about it here, this would have been y equals 0, and this would have been a downshift by 3. Does that make sense? So if you didn't combine it, you could have looked at the asymptote another way, whereas the asymptote, just looking at this, would have been y equals 0 because this is bigger on the bottom and grows faster, but this whole graph has shifted down 3. So instead of being at y equals 0, it would have shifted to y equals -3, which is what we're going to get here. How about that? Okay, so we're connecting dots. That's good. You can find the y-intercepts by solving this. We've got x-intercept here, x-intercept here, y-intercept here. But they didn't label them, they just put them in one list. And then, how did the graph go? So they plotted all those points, point, asymptote, asymptote, and they talked about concavity. They put it all in one chart. I put them in separate charts because I'm just easily confused. But if you want to adopt their nice charting here, you can, and see what's happening with concavity. There's not a max or a min. There's no critical value that's not an asymptote, right? Does that make sense? There can't be a point that's a min or a max. So number 1, this is what confused you. You can't see what I'm writing. Here. Getting the one fraction so you can find the asymptote. Was that what threw you off? Okay. All right, so next one on our list was 7. Let's look at 7. 7. Okay, also separate fractions. Easier to take a derivative with a second fraction because you're doing them as separate units. Then they went and put them together, looks like, to solve it. Here's the graph. Slant asymptote, vertical asymptote. You can't see that here, but there's an asymptote here. I don't know why they didn't draw that in better. I guess they just put this little line there. Caroline. Okay, so slant asymptote, again, if you're looking at this, you'd probably want to put it as one fraction so you could compare the top and the bottom and the growth. If the top is growing faster than the bottom, then it won't be straight. So when we did this last year, we didn't talk about parabolas and other stuff, but just a quick review. So if we had something like x to the 4th plus x over x plus 1, just randomly making stuff up. The top is obviously growing faster, right? Because x to the 4th is going to get really big compared to x. And if you divided this into this, you would say it looked like x cubed. So the end behavior would be x cubed. It's just actually dividing into. When we do asymptotes, that's a line. This is not a line. But when we do asymptotes, it's one bigger on the top. So last year we did this, and y'all were really good at saying, okay, that's going to look like a parabola. That's going to look like x cubed. Well, this one is, if we went back to 7 and figured out common denominator, so y'all didn't think of that trick, and I'm sorry I didn't bring it up yesterday. I'm not sure that's how the book thinks about it, but that's how I do it easier because those rules I know pretty good. So common denominator is going to be x squared. So this is going to be, this has 1 in the bottom now. I need to multiply the first one by x squared over x squared. So it's going to be x cubed plus 32 over x squared. Now the top is 1 bigger. You do long division, and you divide x squared into x cubed plus 32, and you can stop after you get the y equals mx plus b part, because anything that follows after that is going to be a fraction which goes to 0 by asymptote rules. So x squared goes into x cubed. X times, that's x cubed plus, wait, not x times. Yeah, x times. And then that's going to be x cubed. I'm so confused. Oh, there's nothing that goes there. Hello. I got to wake up too. Okay, there's nothing that goes there. So we subtract and we get 0, and we bring this one down, x squared. X squared goes into x squared one time. That's x squared. Change the sign, subtract, we get 0. This would be the remainder. If we want to go all the way out to long division, we would say the remainder over the divisor, just like you did when you said 5 divided by 2 is 2 1/2. The half that you're dividing into goes here, but this goes to 0. Can everybody see it right here? X squared is bigger, and so this asymptote would be 0. As x gets really, really big, this is a teeny tiny fraction like 0. So we disregard this. This is the asymptote y equals x plus 1. So yeah, that's review of the whole rational section that we did last year. And we're going to need long division soon with integrals, so it's good to review it here. Y equals x. Did I write something wrong? 0. Oh, because it's 0. Yeah. 0. 0 x squared plus 0. My bad. Thank you. So obviously that doesn't belong there at all. Okay, so good thing there's an answer key here so y'all could find my mistakes. All right, so we'll all practice long division when we need it again for integrals. So taking the derivatives, that was okay. Finding increasing, decreasing concavity, was that part okay? Was it the rational stuff that we needed to review on? Okay. Yes. So on number 7, okay. Because they turned it into difference of cubes. So if you, so they took a derivative here, which is nice, separate. I mean, that would be easier. I would do that too. So back to my paper. If I combine the derivative, so 1, and then this is 32x to the negative 2, right? So minus 64x to the negative 3, or x cubed. Okay, so if we get a common denominator, that's going to be x cubed over x cubed minus 64 over x cubed. So now we're recalling difference of cubes, which y'all also hate. If you remember SOAP, that helps you. We have x minus 4, and then x squared plus, these two multiplied together, that's 4x plus 16. So SOAP told us it was the same sign here, opposite, same, opposite, and this one was always positive. SOAP, remember that? Okay, so then when you solve this, this is where they got the 4, x equals 4, it equals 0, but this part would be imaginary, just how it works out. You could actually do the quadratic formula and find that out for yourself, but it is imaginary. X equals 4 is a critical number, and x cannot equal 0, so that's also a critical number. That's why they have undefined here. So difference of cubes. Lots of stuff to remember, right? You gotta just pull everything out of your hat, all those tools. And that's why we do these problems and review it, and they're going to start to be fresh for you, so you'll be able to use them again. Okay, so 7. Then if you can plot the minimum, because you can do a test here, and you've got asymptotes, you have things to graph, and you can go from there. So this would have been harder for us last year. We would have had to just guess some points in here. We wouldn't have actually found the minimum. But this, you could find the minimum because you're using 4 as a critical number. How about that? Okay, so what else did we have? We had 7, we had 9, and 11. You want to pick one of those to do from the beginning? Okay, 11. So what's the problem for 11? All right, 11. Okay, while this is up here, the domain, everybody got that? Negative infinity to 4. The things that make it negative, but you can have it to be 0. So, big. So we've got domain. We're only going to have to graph up to this. We're not going to graph 4 to infinity because x doesn't exist there. We're going to take a derivative. How do we do that? Product rule. So first, derivative of the second is going to be 1/2 4 minus x to the negative 1/2 times negative 1. So this was taking a derivative with product rule and chain rule, and then we've got to do plus. We keep the 4 minus x to the 1/2 power and do the derivative of x, which is just 1. Back to chapter 1 of last year. When we're trying to solve for this and finding critical numbers, we need to factor out things that are common. We're going to factor out 4 minus x. Are we taking out to the negative 1/2 or the positive 1/2? To the negative 1/2. We take out the smallest power. That's going to leave 1/2 x, because this is gone. It's actually negative. And then this one, we're taking out negative 1/2, which means we have 4 minus x to the first power. All over nothing, because it's not quotient rule. Sorry, I just don't want to forget that. So now look at the derivative. You can solve from here. It's not pretty, like I can combine stuff, but I can find critical numbers. Somebody give me one of them. 4. 4 is a critical number because this is going to be in the denominator, and that would make it 0. It's okay to be in the top, so it's part of our domain, but it's not allowed to be in the bottom. So we've got x equals 4 as a critical number, undefined if someone asked you. And this one we're going to solve negative 1/2 x plus 4 minus x equals 0, the top equal to 0. So I've got negative 3/2 x equals negative 4 multiplied by negative 2/3. How about that? Adding fractions, moving over, multiplying, x equals negative, positive, 8/3. 8/3. Critical numbers. There we go. What's next? Okay, so sign chart. I'm going to put the simplified version up. So what's that? Negative 3/2 x plus 4. And then the denominator, so that's the square root of 4 minus x. And I've got, oh wait, 8/3. Is that in my domain? Yes, it is. Okay. 2 and 2/3. Okay, just want to make sure. 8/3 and 4. Number smaller than 8/3. Go. 0. 0 in the top is positive. 0 in the bottom is positive. This is positive. So this is increasing to 8/3. And after we've got 3. 3 would be negative 9/2 plus 4. What's that? Negative. And then 3 would be 4 minus 3 is positive. This is negative. So this is decreasing. So at 8/3, what do you have? So if this is derivative, we're saying that the function is going to go up and then go down at 8/3. So it's a maximum. So this is a max. And you need to find the point. So how do you find the point? Plug it back into here. So we actually have to find the point. Y equals 8/3 times the square root of 4 minus 8/3. Did they find some decimal for that? Or that 12 minus 8. That doesn't come out pretty, does it? 16 square root of 3/9, which we still probably want to have something we can graph. I wish I had a calculator. What is that in a calculator? So yeah, we could graph this on a calculator, but I mean, this math is hard. It's okay. We're going to pull out a calculator. Is this going to be a multiple choice question on your exam? No, it's taking us 15 minutes to do. But we're understanding the math, and that's fantastic. Let's see. 8 divided by 3 equals, what you got? 3.079, 8/3. Okay, so we have a maximum. Fantastic. How do we find concavity? We take a second derivative. So this was what it looked like on the top. I'm going to rewrite it so it's pretty. Y prime, what's not that pretty? Negative 3/2 x plus 4. 4 minus x to the 1/2 power. So y prime, double prime, is going to be bottom, derivative of the top. Bottom. 4 minus x, keep the 1/2. Derivative of the top is negative 3/2. Everybody concur? Concur. Bottom derivative of the top minus top. That's going to turn into a plus. And then minus 4. Oh, I'm not going to do that. That's too confusing. Minus negative 3/2 plus 4. Derivative of the bottom, 1/2. 4 minus x to the negative 1/2 to the negative 1. Yay! Over 4 minus x. At least we got rid of that on the bottom. But it's coming back. So we did these ugly derivatives when we first learned derivatives. They may not have been our second derivative, but we did these longer derivatives. Now we've got to simplify the top. Take a second. Work on it yourself. See what you can do by yourself, because that's the only way you're going to know if you know how to do it. So if you're watching on video, pause the video, work on simplifying the top so that you can put 4 minus x to the negative 1/2 on the bottom and simplify so you can solve. There are actually several ways you could factor it. We're going to take out at least the 4 minus x to the negative 1/2 on the top. Your book would probably take out the fraction, so they'd take out a 1/2 as well. And it's up to you how detailed you want to factor it out. We can still solve with the fraction in the top, so I don't want to lose you in the factoring part. So I'm just going to take out the 4 minus x to the 1/2, or negative 1/2. Is that okay? All right. So y double prime. I'm going to take out this guy right here, 4 minus x to the negative 1/2. So I'm going to be left with this one becomes 1. So I have 4 minus x. And I still have this, negative 3/2. Okay? Then I'm taking this out entirely. The negative 1 and this negative make a positive, so I'm going to do that here. I've got 1/2 times negative 3/2 x plus 4. How's that? It's all over 4 minus x, but for space's sake, I'm just going to keep remembering that until I move it down in a sec, because I want to simplify this bad boy. How we doing? Okay. So it has a fraction there. Okay, so y double prime, I'll put this down here now, 4 minus x to the 1/2 times 4 minus x. Bless you. So I just moved this to the bottom, and I kept the 4 minus x that I had for the other one. If we distribute here, then I have negative 6, because negative 12 over 2, and then positive 3/2 x, and then negative 3/4 x plus 2. How's that? Y'all have already done it, so is that right? Okay. These make negative 4, negative 4. If I make this 6/4, I can say 6/4 minus 3/4 is positive 3/4 x. All over 4 minus x to the 3/2 now. Yes. From this step or before this step? Okay, so negative 6 plus 2 is negative 4. And then this was 3/2, and I made it 6/4. I made it 6/4, and I didn't want to rewrite the whole thing, so I just wrote it over top. Now I have them both in fourths. 6 minus 3 is 3/4, and it's positive. Okay. And then these two together, they have the same base, so you can add the exponents. 1/2 plus 1 is 3/2. Now, what are we doing? We're trying to find points of inflection. So we're going to say that x cannot be 4 in the bottom. We still have a square root here, so x cannot be 4. That's not going to be a point of inflection, but it's where concavity might change. It's actually the end of my graph, so it's okay as far as figuring out concavity around it. And then the other one is going to be negative 4 equals, oops, not equals, negative 4 plus 3/4 x equals 0. 3/4 x equals 4 times, flip it over, 4/3 x equals 16/3. That's a possible point of inflection where the concavity is going to change. Is that in my domain? No. Okay, so it's not going to graph at all. So not in domain. Domain is huge. I focused on it a lot last year because I know how huge it is, but starting from the beginning, you should note domain, and then as you find stuff, you can toss it out if it doesn't have relevance for your graph at all. Okay, so what do we know? Do we have any x or y intercepts? So if we plug in 0 for y, and then we say x times 4 minus x, or 0 equals x times 4 minus x to the 1/2, it looks factored like this, and you can solve for it. So do we have any x-intercepts? 0 and 4. So when you solve these two equations, you have x equals 0 and x equals 4. We have x-intercepts. We have something to graph. Hallelujah. How about plugging in 0 for x? We also have the y-intercept is 0, 0. That always happens when you have this being 0, by the way. But okay, let's see what we got so far. We have a point at 0, 0, a point at 4, 0, 1, 2, 3, 4. What else do we know? It can't be more than 4, so this is the end of my graph. What else? There we go, 8/3, so max, we found on the other page, my other page, 8/3, so that's 2 2/3. 2 2/3, comma, 3-ish. So 2 2/3, 1, 2, 3 is a max. What else do we know? We know that it is increasing to that max and then decreasing after the max. There's no point of concavity, but like point of inflection, but we could take that second derivative, which was -4 plus 3/4 x over 4 minus x to the 3/2, and we could find out the concavity by checking any number. So tell me about numbers we could plug in. So -1. We have 4. That was the only point that we had that was in our domain. Remember, the other point wasn't in our domain. So we can test anything. 0 might even be my favorite because it's going to be negative. The bottom is always positive because it's got a square root. The top, in our situation, is always going to be negative because if you plug in 0, you get -4. If you plug in -1, you're going to have -4 3/4. Whatever you plug in is going to be negative. Does this look like negative concavity? Okay. And it didn't change concavity because the other point would have been outside of our domain. So what does theirs look like? Is mine pretty? Let's see. Oh, look. So you have way more skills than you had before. If you were just doing an XY chart in pre-calculus, you wouldn't know to go to 8/3. You wouldn't have been able to find this exact max. Mine's not pointed. This exact max. But you would have found the x-intercepts, and you might have tested some points, and you would have gotten domain right. But it still would have been hard to guess what things to plug in. Notice how there's not a derivative here at 4 because there's nothing to the right of it. So that was why that was a possible point of inflection, or I'm sorry, a possible critical point where it was undefined. Because that would have been a sharp turn if we'd have multiplied by something else. Okay, so you had another one, I think 9 or something to try. Maybe try that again tonight for homework. I do want to look at some graphs today. So here's what I'm taking away from looking at your notes and the questions that you've asked me, was that I do feel like you have the skills to do this. There were not a tremendous amount of problems. There were some ones after this that we might need to talk about some more tomorrow, but we've still got this section tomorrow, so I'll leave that open. But you've had all the skills to do this. You needed a refresher on some of the older stuff just to do that better. And now that you're like, notice that there's things that didn't come as easily maybe last night. Today's, you had good questions, and you can go from here and do better. But it's not as if you don't have the tools to do this. It's just putting it all together and making it make sense, I feel like. So I think with some more practice, you're going to be cool. All right. I do want to look at some graphs, and I had at least one person ask about, I guess, what was it, 71? Was that one of the graphs? 71. Yeah. Okay, so let's look at the graphs, and that's what I wanted to do as far as new stuff today before you have new homework in this section. So 71, 71 was given to you as a graph, and they told you that use the graph of f prime, and it goes to -4, I think. 1, 2, 3, 4, and 2. 1, 2, 1, 2. Okay, they tell you this is f prime, and they want us to sketch the graph of f and the graph of f double prime. So here's the thing. When we sketch the graph of f, we're not going to know exactly where it lives. In other words, if this is the derivative, I could take, and this has an equation, I could actually figure that out. It's probably x squared minus 4, because it looks like a parabola. It goes down 4. It has x-intercepts at 2 and -2. So I know what this derivative is. I know the original equation is probably what? X cubed. And in order for me to, and this is going to come up soon, we're actually going to go backwards and figure out what f is. But you have the thought process to say, okay, if this is the second degree, then the original one was the third degree because they go down, so it's going to be x cubed. It's actually going to be not just x cubed, it's going to have another number there, but that's not important right at the moment. What is the 4? What would the 4 be? What would you take a derivative of to get -4? What? Minus 4x. So this one's right. If I take this derivative right now, I don't get x squared. What do I get if I took this derivative right now? 3x squared. So what did this need to be so that I get x squared? 1/3 x cubed. Perfect. Okay, so the one thing we don't know is what? We don't know where it lives, what the shift is. So this -4 shifted my parabola down 4. This could have anything here. It could be +2. It could be +22. It could be +12. I don't have any idea because when we take a derivative of a constant, it's 0. Does that make sense? So when we graph the original function, we're graphing its shape. We don't know where it is vertically. And I'm going to keep saying that, but eventually it'll sink in. All right, so graphing the original function, I normally just do it around the x-axis because that makes the most sense to me. I do know that this value, if this is the first derivative, then I can describe my function. So that means that right here, this is the first derivative, and these are positive values. This means slope is positive here. M is greater than 0. Slope is positive on this side of 2, -2. So at -2, I'm going to have positive slope. And right here, where I have f prime, where does f prime equal 0? -2 and 2. If you look at those two values, those critical numbers are either mins or maxes usually. So these are the critical numbers. Tell me about -2. The slope goes from positive to negative. So what is -2? It's a maximum. So this is a maximum. It's increasing. It has positive slope and then decreasing. Voila. What happens at +2? It's 0 here. It goes from negative to positive. So at +2, this is a max, this is a min. At +2, it's a minimum. It's just a minimum, and then it goes up again. And I have positive slope, positive slope, positive slope, positive slope after 2, positive slope. How am I doing? I'm trying to connect these ideas. Making sense a little? Okay. And then this is all negative slope because this is the slope graph. This is negative slope. negative slope. I don't know much more than that. It's the slope graph. And so now I have a third degree function, and we figured out what it should look like. We could make it better, except for the constant, the shift. But there you go. This is f. So you need to take your slope graph, and you need to think of it as slope. Positive slope, negative slope, positive slope, and where f prime is equal to 0, those are mins and maxes. You know everything. We just have been doing it from the function, not the graph. So we just have to connect those two ideas. Okay, so now we're talking about the second derivative. What does the second derivative tell us? It's the slope of the first derivative. That's one way to look at it. You could also probably graph it from this one, but we weren't given this one. We made it up. So maybe we should stick with this one. So it's the slope of f prime. So tell me about the slope of f prime. It has two different slopes. It goes, the slope is, it's decreasing until 0. F double prime is less than 0 from negative infinity to 0. Or you could say f prime is decreasing. Remember, decreasing describes, it takes it to the next level. It is the derivative. This makes it second derivative by using decreasing. So that means if we were to graph it, when we get to 0, is it ever 0? When is it 0? When is the second derivative equal to 0? At 0. At the minimum of the first derivative. So it's 0 here. I can actually put a point at 0, 0. It's 0 at 0. It's a point, 0, 0. And it's decreasing before that, which means it's less than 0, and it's negative. On this side, it's increasing. That means it's positive. And if you want to be specific, it is a straight line because this is second degree and this is first degree. It means that the acceleration has a constant slope, which is jerk. Yeah. So there's a whole list, and I want to put that up on the board because that's really interesting to me, what the names are of the fourth derivative, third derivative, fourth derivative. It goes jerk, and then is it snap, crackle, pop? I don't know. We looked at it, but I don't remember. Okay, I'll put that up because I think that's humorous. Okay, so 71. We talked a lot about that. But connecting those ideas, you probably need to make a list. You probably need to draw it and write on it and think about all the things you would if it had been a regular function. Tonight for homework, you have some of the other graphs. Let's see what you have. So let's look at 70, because 70 is not one of your homework problems. 70 says this. I think it's at 1 and negative 1. Pretend that this is pretty. Okay, so 70 says, the graph of the second derivative of f is shown in the figure. Use the graph to find the intervals on which the graph is concave up or concave down. So A, concave up, concave down. So if this is the second derivative, we're looking at its positives and negatives. So where's it concave up? Negative 1 to 1, where it's positive. So concave up, negative 1 to 1. Concavity, we're going to use open brackets because we drew concavity yesterday, and it changes at the inflection point. So at 0, we're not including it, or at where this is 0, at 1, we're not including that. Concave down, it's negative over here and over here, so I'm going to say negative infinity to negative 1, and 1 to infinity. You don't really use a union sign because we're just saying that this is an interval and this is another interval. We're not like mashing them together. So I would just put a comma. And then B says the intervals on which f prime is increasing or decreasing. B, f prime is increasing, f prime is decreasing. So describe for me what f prime is increasing means. The slope of the first derivative, which is the second derivative, is positive. So the same answer, yeah. But the idea of presenting it in a different way and knowing that that means the same thing. So this means decreasing, which means its derivative. So it means the second derivative is negative or the second derivative is positive, which is the same thing as concave up and concave down. So these are the same answers. Okay, and then it says C, the x values at which the graph has a point of inflection. C, x values of the point of inflection. In order for it to be a point of inflection, it has to change concavity. And what has to be equal to 0? It's the x-intercepts on the second derivative. So we're going to say f double prime of x equals 0 at, so 0, it's 0 on our graph, at negative 1, x equals negative 1 and positive 1, and does it change signs there? Yes, so this is negative to positive and positive to negative, so yes. But it does have to change sign. So if your graph bounces there, it wouldn't change sign. How about that? Does that make sense? All right. Just like a min or a max, it can be a critical value, but if it doesn't change sign, it's not a min or a max. It would be increasing and then increasing some more, so not a max. And that's the deal for 70. So the idea is that you have to figure out what graph it is and apply the math that you know, the equal 0, the positive negative, what that means as far as increasing, decreasing. Note that they asked for the x value for this. They didn't ask for a point because we don't know a point, because we don't know where the original function lives. We don't have enough information for that. So you can't give a point. If you gave a point, they would count it wrong. Some people would say negative 1, 0. They'd give a point. That's the point on the second derivative. It's not the point on f. These are points of inflection on f using f double prime. Does that work for you? Okay. So what you have for homework are, go back and try, I think it was number 9 again. If there are others, there are a couple other problems that we didn't go over. Check and see if you can think through those now that you have, we've talked through a lot more stuff today. And then try the new problems that you have for homework. There's going to be some trig in there. I don't mind if you use your calculator to find points, but you're going to have to do the work, which is taking a derivative and trying to solve trig equations. And I don't know, let's see. There's some odds, so, you can go to the little video and it will help you through it. And we're going to go through more stuff tomorrow. But But as much as you can work through on your own, you're going to make those connections, which is why I wanted to pause and stop and let you work on factoring earlier, because it's better if you do it. All right, and that's it.